Hi everyone. So now let's start linear regression with gradient descent. Okay. So some of you might not be knowing this algorithm. So that's why let's just do one thing. We will be seeing this algorithm today only, which means that at least a quick recap we will be seeing. And if you want to solve just more questions, then you can watch the complete video on gradient descent that we have taken in the calculus, and also I have put in the machine learning course. Okay, so if you want, you can watch that video. That video just might be having more questions than we will be covering today regarding the gradient descent. Okay, this is a general technique. So we will be studying the gradient descent from scratch today also. And also, if you want, then you can watch that video. It will be just having more questions. That's all. Okay, regarding the gradient descent, and then we will be seeing linear regression with gradient descent. Okay. Okay, so before I start the gradient descent, let me just tell you there is one very important property of gradient. This is extremely important property of gradient, which is that let's suppose you have some multivariate function, right? Let's suppose you have this multivariate function where you have there is a x-axis, for example. Okay, there is an x-axis, there is a y-axis, right? And there will be z-axis. So suppose on x you have w1. Here let's suppose you have w2. Here let's suppose you can be having the loss function, which is let's suppose these are w0 and w1. Okay, maybe let's suppose w0 and w1. So on the z axis you have the loss function, which is a function of w0 on w0 and w1. Now, clearly, this is a 3D picture in the sense that you have three axes here. Two are for the weights, which are W0 and W1, and third axis is for the loss function. Okay. If there is, let's suppose, more weights, or if there is a multi-dimension, then you will be having even more axes, which is impossible to draw in this 2D surface. Okay. Although like 3D plot is not even possible, like you can say with 100% efficiency, but yeah, we can make our efforts to show 3D plots. But if you go beyond 3D, it is impossible to draw on the 2D surface, right? So that's why, like, just imagine that. I mean, then just consider the 3D plots only. The similar things will be there in the 4D, 5D, like that. And if you want to imagine, then let me just tell you, if you want to imagine 3D, more than 3D, like 4D, 5D, 6D, 7D, 8D, then it is not even possible to imagine. Okay, you won't be able to even imagine that how it might be looking like, because in our real life we only see 3D objects. Is this fine? Okay. Now let's suppose you have this function. Is this function okay to everyone? Now this function is having, suppose, maybe let's suppose here you are having the loss. Okay, just for the visualization purpose, let's suppose on the z axis you have just w uh, w naught, w1. Okay, suppose this is your w1, and suppose your loss is here, which is w naught and w1. Now tell me, here the loss is more, or here the loss is more? Let's suppose this is point A and this is point B. At which point do you see the loss is more? Obviously at point A, right? I mean, since it is vertically growing, so obviously at point A, right? The loss is more, right? Anyway, so suppose that I'm here, right? I'm here at some point in time, and I ask you that in which direction I should be going. Direction in the sense that with respect to W0 and W1, I'm asking, right? So in which direction I should be going such that my loss decrease? Then definitely you might say that with respect to w0 I should be going right. If I just ask you with respect to the x direction, in the x direction, where should I be going? Probably, if I'm standing here, right, immediately you tell me, in the sense that if I just ask you with the immediate step, in the sense that if I just go little left or little right, let's suppose there are only two options, either little left or little right. Okay, so in the sense that I want to move in parallel to x axis, then what will you say? Okay, little right, right? It is possible that if I increase the value of w naught, then probably the loss is decreasing, right? So tell me, is loss decreasing in this direction, in the sense that if I keep everything constant and I just move in the direction of w naught? Yes, it is decreasing in this direction, right? Tell me, is loss. Now you might not be able to visualize it too much, but suppose I go in this direction also, but at the same time I also go in this direction, which means I decrease W naught and W1 both. Probably I go in this direction. Will you be decreasing the loss? Are you getting my point? So is this direction X direction? Is this a X direction? No, right? Is this a bidirection? No. Is this a Z direction? No. This is neither X, Y, or Z. It is a mix of them. Which means you can say it is probably some in some X, some Z or something like this, right? It is not neither X nor Z. It is a mix of it, right? Understood? Okay. So you agree with me that at standing at this point, if I see in calculus, we always ask a question in the sense of neighborhood, in which means that if I'm standing here, then you tell me that by checking the neighborhood, you will tell me that okay, if you go like this, probably go like this, then there are multiple possible directions in which you will be decreasing your loss function. Is this fine? Okay. So there are multiple possible directions. That is fine. Now, if someone asks me that what is the direction where I will be decreasing my loss function with the maximum efficiency, in the sense that if I go there, then my loss function will be decreased too much. For example, if I just go in this direction, do you think my loss function will be decreased too much? In the sense, if I just go, let's suppose, in this direction, almost same, little, okay, just go little, okay, almost same, right? But if I go, probably let's suppose this is some tangent or something, but if I go, let's suppose, okay, in this direction, probably it is more decrease compared to this direction. Do you all agree? Right? So just see visually here, right? I mean, don't worry about the mathematics, just see visually that there are multiple possible directions in which it can decrease, but this direction is better compared to at least this direction, right? So if someone asks you that what is the best direction in which I should be going, that I should be decreasing the most, so that is given by the gradient direction, okay, or the negative of the gradient direction. So the function increases the most rapidly in the direction of gradient, function decreases most rapidly in the direction of negative gradient. It is very, very important property of the gradient vector. Okay. For example, that this multivariate function is given to you. Suppose I say that here at this particular point, the gradient will be, let's suppose this function could be, okay, something, maybe W1 x1 plus W naught whole square plus, I mean, some function will be there, right? So basically, let's suppose this is the function. Now, if you find out the gradient of this, it will be of which, how many dimensions? The gradient will be in how many dimensions? 3, 4, 2, 1, 2 dimensions, right? It will be like this with respect to W naught, with respect to W1, right? It will be like this. It will be in 2 dimension. So the gradient is in 2 dimensions. So gradient is a vector which is a 2 dimensional vector currently in this case, right? Now, yes, gradient is also slope if you talk in case of 2D. Okay. Now, tell me, whatever is the value of this, okay, tell me if I take the gradient at, let's suppose, W naught and W1 at some value, let's suppose 1 comma 5, will it be all, I mean, will the gradient direction be always same, or it might depend on the point whether I'm at 1 comma 5? I mean, this will be the function of W naught W1, or it will be just same for this particular function, for this particular loss function. It will depend on the point, right? I mean, for example, at this point maybe the gradient direction is this, at this point maybe the gradient direction is this, or whatever, right? So the gradient direction will depend on the point to point. Okay. So if someone asks me that given this point, given this point, where should I be going, that I should be increasing the most, then what will I do? At this point, I will be finding out the gradient of this function. Okay. At this particular point. Okay. Let's suppose this is W equal to W, uh, whatever, right? W naught, or maybe W tilde. Okay. So basically at this particular point, which is a W tilde, right? Then I will do what? I will find out the gradient at this particular point. Okay. At this given point. And this direction, the gradient direction, wherever it will tell me that, okay, if I go in this direction, the function will be increasing the most. So can you find out the direction of the gradient easily, right? Let's suppose this is 2 and this is -5. Then what does this mean? It means that if it is 2 and then this is -5, it means 2 means, I think, somewhere here -5 quite be, I mean, behind this, board. If it is positive direction I'm considering, -5 could be there. So maybe 2 minus 5 could be a vector which is something like this, right? Okay, anyway, like, that, that how to draw, right? 2 minus 5. So 2 minus 5 is not very hard to find out. So if you know the gradient, then you can find out the direction of this also, right? Is this fine to everyone? Okay. Just like we have been doing in case of 2D. Like, if you know this, then you know the direction of this. Now, what you want to do, given at this particular point, you can find out the direction of the gradient. Okay. Let's suppose it is in this direction. Then you know that where to go such that it will increase the most. Okay. And similarly, this the second property is also very, very important, that if you go in the opposite direction of the gradient, then it will decrease the most. That's called steepest descent direction. Okay. So this direction where the function is decreasing the most, it is called steepest descent direction. Okay. For example, let me just give you a very familiar example. Here, this gradient is in 2D or 3D. You just told me it is in 2D, right? Now I'm taking a gradient with respect to W0 and W1. Okay, that's why it is in 2D. Now suppose my loss function is just like this, very simple loss function. Okay, or maybe any other function which is just in 2D. Okay, suppose, okay. So how many parameters I have here? How many parameters I have? Only one parameter. Now, in this case, if I just ask you that, if you find out the gradient, let's suppose this is just W square or something, right? If you find out the gradient, then it will be how many dimensions? Just 1D, right? It will be just a scalar number, right? So gradient will be either in the direction of W or in the direction of negative W. I mean, it will be in this space, right? For example, here, if you ask me, in this particular case, if you ask me about the gradient, then gradient is in the direction of which x, y, x, z, y, z. Can you tell me? Gradient is in the direction of, maybe you can see this, or maybe this is in the direction of x, z, right? X, z. Okay. Why? Because I'm taking with respect to the parameters. The parameters are in the x, z directions. Okay. So here, if I take the gradient, it will be in the which direction? It will be in the direction of W, right? So here the gradient is just, you can say scalar, which is fine. But in case of the direction, if you take it as a, the directional quantity, then it will be in the direction of W only. Suppose this W is 3. Can you tell me the gradient of this loss function, which is actually 2W, but at the point of 3, can you tell me? 6, right? So it will be, the gradient will be 6, right? Tell me, this is positive direction or the negative direction? 6 is plus or negative? It is positive direction. So what does our rule say? What does our rule say? If we go in the direction of gradient, when the in the sense the direction is this, right? Gradient direction is this. So if we go in the direction of gradient, then the function should be increasing or decreasing. So this is direction of gradient. The function should be increasing, which is written here. Okay, this is the rule which is not very hard to prove. It is easy to prove only. We have proved in the calculus, but for now I'm skipping the proof because it's not required. Okay, and if you have not watched the calculus lecture, it is fine, because it's not needed to prove it here. Okay, we have already proved it, but that's fine. So basically, this is the direction of gradient. So if you go in this direction, function is definitely increasing, right? Now let's just take one more example. suppose you are at this point, which is, let's suppose, -5. At this point, can you tell me what is the value of the gradient? -10. Is this okay to everyone? Now, what is the direction of gradient? This one, right? So this is the direction of gradient. Tell me, if you go in this direction, is your function increasing? Yes, right. If you go in this direction, function is increasing. Now just verify the opposite rule, which is that if you go in the direction, in the opposite direction of the gradient, then is the function decreasing? If you go in this opposite direction, is the function decreasing? If you go in the opposite direction, which is this, is the function decreasing? Yes, right. Now tell me, if you go in the opposite direction, the function is decreasing, which is fine. But see, if I go like this, if I go in this direction, I mean like this, then function seems to be, increasing, right? I mean the function could be increasing if you go like this. Okay, for example, if you go too far, if you go here, in this direction I want to go, but if I go here, then the function value, let's suppose this is 100, the function value will be 100 square, right? Function is increasing. Is this fine? So where does this lag? Where does this rule get disturbed? Yes. So in calculus, we always talk about the local things, the neighborhoods. Okay. Generally, there is no rule which talk about the global minima or the global maxima. We always and always talk about, even we do the calculus module one, in the sense that, I mean, just gate CSE calculus. If I just try to minimize, maximize, or whatever, then whenever we define limit, okay, you might have seen limits, right? X plus h, like this, right? Where h tends to 0, like this. So whenever we define limit, whenever we define differentiability, whenever we say, okay, it is a minima or maxima, we always talk in the sense of neighborhoods. Okay, so I can't go too much. Obviously, if I go too much, then anything can happen. But if I just see in the surrounding, okay, if I see in the surrounding of -5, just a neighborhood, then if I go left, it is definitely increasing. If I go right, it is decreasing, isn't it? Is this fine to everyone? So if you go too much, then anything can happen for sure. Okay. So if anyone is having doubt that, okay, if I go too much, then it is 100 and 100 square is there. But here it is just -5 square. It is just 25, but it is 100 square, which is too high value. So it is increasing, even if you're going in the opposite direction of the gradient, right? So if you go in the opposite direction of gradient, then it should be decreasing. And that is true only when you're talking in the local sense. Okay. You're talking about the neighborhood. Is this fine? Cool. Okay. So now let's just move to the property that if you go in the direction of gradient, it will be increasing. If you go in the direction opposite direction of the gradient, it will be decreasing. Okay. So for any multivariate function, given this particular point, okay, let's not talk about this. First, let's talk about this. Given this particular point, in how many directions you can go, where your parameter can change your loss function or your function, in how many directions you can go? Only two directions, right? I mean, either you can go right or you can go left. Only two directions are possible, because there is only one parameter. Only two directions are possible here. But here, at this particular point, how many directions are possible? If you are at this particular point, how many directions are possible? Here, either you can go x, maybe you can go y, you can go z, or like this, right? So how many directions are possible? Actually, infinitely many. Yes. So you don't just need to go in the X, right? It is just like, a 2D plane surface. Let's suppose this is your room. You are in the center of your room. Is this necessary? You will be walking in this direction only, or this direction only, or this direction only, or this direction only. There are infinitely possible directions in which you can walk. Is this true? Right? Suppose you are at the center of your room, and then someone asks you that, okay, move just in particular direction, how many possible directions in which you can go, then theoretically you will say that there are infinite possible directions, right? So Yashasvi is saying like north, east, west, south. No, like, but you can always go with the southwest, right? At what angle you are going, it also matters, right? So is this fine to everyone? You can go in any direction. Okay. So Anurag, I will just ask you to please pay attention here. Why it is decreasing? Why it is decreasing? Because if you go to the opposite direction of the gradient, right, then it will decrease, which means that if we are going the direction of the gradient, it is increasing, the function is increasing. If you go to the opposite direction, which means if you go in this direction of the w, then the function value is decreasing. Okay. So is this thumb rule okay to everyone? This thumb rule is extremely important, right? Now just tell me one thing. No, don't. What is this? Don't compare the value of the loss function, which is minus 10 or something. Compare the value of, sorry, no, don't compare the value of the gradient. Compare the value of loss function. Okay. So loss is decreasing or increasing, the what is happening about the gradient, it doesn't matter, right? So the gradient is, I think, anyway increasing minus 10, and it could be even better, and finally it is zero. Right? The gradient could be increasing, but let's not worry about the gradient. I mean, the value of grad L doesn't matter. The value of L matters. Okay. Okay. So now just tell me that you are, let's suppose, at some point, right? And let's suppose this is the direction of the gradient. Okay. Suppose this is the direction of gradient. Now tell me what is the direction in which it will be increasing the most. This direction, right? Most increase. What is the direction in which it will be decreasing the most? This direction, right? Okay. Now just tell me, suppose this is 90-degree angle. I mean, with the gradient, let's suppose I'm forming 90-degree angle. Suppose if I go in this direction, what will happen? I'm not going in the increasing, neither in the decreasing. If I go perpendicular to the gradient, then yeah, function value won't change in this direction. Okay. For example, for example, let's suppose this is the case. Now, since this is the loss function, now just imagine that I'm just cutting it. Okay, just I'm cutting it like this, which means in the parallel to y-axis, if I'm just cutting it with a disc or something, then then there will be a circle kind of thing. Can you imagine? There will be a circle kind of thing if I just cut it and just see it from the top. At that circle, at that particular circle, can you imagine that the value of the loss function will be same at the whole circle? Because since you're cutting it, right? Since you're cutting it, so basically it's like this. I have images. So yeah. So for example, I'm just cutting it. Okay. Then there will be a circle. At that particular circle, since this value, okay, this value of z is, let's suppose, 1. Okay, z equal to 1 is here. Then at the whole circle, z will be 1, right? Okay. So basically what I'm saying, let's suppose you are here, and if you go in the if you go in the circular motion, or in some direction here, such that the function value is not changing, that means you are most probably going in the perpendicular direction of the gradient, because then only it is possible. Do you all agree? If you are going in this direction, then the function value is not changing, right? Right. then it means this direction should be the perpendicular value, perpendicular direction to the gradient. Okay. So basically there are directions in which the function value actually doesn't change, which is the perpendicular direction of the gradient. Now, if you go in, let's suppose this direction, then do you think the function value will be changing? Won't change, right? Because this is the perpendicular direction of the gradient. Now suppose if I just ask you, imagine that if you go in this direction, what do you think? Will the function value will be changing or not? If you go in this direction, will it be increasing? The function is increasing, or do you think it will be decreasing? Increasing only, right? Basically, if you go anywhere in this region, the function will be increasing. If you go anywhere in this region, the function value will be decreasing. But but suppose I have the option to increase the function by going in some direction, or to decrease the function by going in some direction, and I'm in hurry. Should I be going to the direction which is the most efficient, or I should be taking some random direction of increase or maybe of decrease? Okay, tell me. Obviously the most efficient, right? So if I want to decrease the function, and given that I'm at this particular point, what will I do? If I want to decrease the function, and given that I'm at certain point, some w, let's suppose w, uh what should I call it, wt. Okay, at, okay, just it is just a variable name, wt. Okay, don't worry about this t and all, it is just a variable name. Okay, just to differentiate from w. Then what will I do? I will find out the uh, gradient of the function at wt, and then I will go in the opposite direction of gradient. Is this fine to everyone? I will go in this direction. Let me know. So this is the direction to move, right? Okay. Now, I hope we have set up the base for the gradient descent, in the sense that gradient descent is one algorithm that iteratively goes to the solution. Okay, which means we have seen how to go to the solution like a closed form solution. What was that? I mean, for the linear regression, if you remember, then it is we want to solve this, right? X w equal to y. So just multiply x transpose both side, and then you will get to know the normal equations, right? So this is the normal equations. Suppose that x transpose x inverse exists. In that case, actually mostly it will exist only, because mostly x columns of x are linearly independent. So in that case, you can say it will be something like this. Is this fine to everyone? So this is called closed form solution. Anurag is asking, is the loss function the same as linear regression loss function? No, I'm not started the linear regression here. I just took some. This need not to be a loss function. It could be a gain function. It could be anything, right? It is just a function. Okay, if you're not comfortable with the w, you can take it as x. It is just a function. Okay, fx, which is x square. Okay, it's just a function. Okay, so this is called closed form solution, in the sense that you directly got your answer. But gradient descent is a way where it doesn't directly tell you the answer. It will say that, okay, let's just do one thing. Let's start. Okay, let's guess your initial w, maybe at here, which means you will guess that, okay, your minima is here. Is this the minima point? No, right? Since it is not the minima point, then the gradient descent will just first guess the initial guess, and then it will help you to go in the direction where the function is decreasing. How? In the opposite direction of the gradient. Okay, so you go in the opposite direction of the gradient, which is this, which means you go from here to here. Then you say, okay, now where to go? Opposite direction of the gradient. Okay, here to here. Now let's suppose where to go? Opposite direction of the gradient. Suppose by chance you go too far. Okay, let's suppose you go here. Then from here where to go? Opposite direction of the gradient, which is right, right? From here where to go? Opposite direction of the gradient, which is right. And then eventually you will get the solution that okay, here the gradient is zero. It means that now we have arrived at the solution. Is the plot clear, everyone? That what I'm trying to say? Okay. So you will keep on going in the opposite direction of the gradient, right? You will keep on going in the opposite direction of the gradient, which is called gradient descent. Now, before we talk about the gradient descent, let me just quickly talk about something called as contours. Okay. And then we will talk about gradient descent. Why I'm calling it detour? Because there are two reasons. Actually, it is a detour in the sense that it is not the actual thing that we want to discuss today. So that's it. That is why it is a detour. And why it is a quick? Because I have already discussed in the calculus. Okay. So if you have not watched those lectures, that's fine. I'm again having it here. Okay. So let's just quickly see what is a contour. It's just a simple definition. Very easy definition. Contour or level curves are the same thing. Basically, sometimes I might use contours or sometimes I might use level curves. So these are the curves of a function, set of curves, uh, where I will be basically doing one thing. Let me just show you. See, let's suppose this is my function, right? Now, what will I do? I will just cut this function. Okay, let's suppose this is my function, which is the loss function. I mean, any function need not to be loss function or anything. Xy. Okay, this is z equal to xy. Now, what will I do? I will cut this function. I will chop it out like this. Okay, and then I will be getting many circles, right? If I keep on chopping it out, I will be getting many circles. These circles are called contours, right? This, these circles are called contours. Is this fine to everyone? For example, for example, if this is my 3D plot, okay, if I keep on cutting, okay, keep on cutting, then sometimes I might be getting a smaller circle, sometimes I might be getting larger circle, which is fine, right? So tell me, if I cut, then I will be getting like this, right? So tell me the smaller circle I'm getting at top or bottom? Smaller circles I'm getting at the top in this case, right? I'm getting at the top. Okay. Here in this case also I'm got smaller circles are at the top, which is fine. Now, if I cut like this, now here the smaller circles are at the bottom, okay, which is also fine. Okay. So here, let's suppose these are the z values. Now, smaller circles are at the bottom. So let's suppose this is z equal to 1, this is z equal to 2, z equal to 3, z equal to 4, like this. Okay. So I'm basically drawing it like here. Don't worry, let me just clear it more. For example, if you keep on cutting, you will be getting something like this. Okay. Okay. Now, if I just ask you, looking at this, if I just ask you that suppose this value of z, the innermost z equal to k1, the outermost z equal to k2. See, at one circle, the value of z will be same. Do you all agree? For one circle, for example, here z is 1, then it won't happen that, okay, here it is 1, here it is 2, here like this. At one circle, the value of z will be same, right? Is this fine? For the one contour, the value of z will be same. Now, suppose this z value is k1 and this z value is k2. Can you tell me k1 is greater than k2 or k2 is greater than k1? Which one is true? Which one is true? See, here, the smaller circle is at the top, right? It means it must be having the higher value. So basically, the smaller circle or the the innermost circle is actually belong to the top. That's what I want to say, right? Top means the higher value. So K1 is greater than T2, right? K1 is greater than K2. Why that is the case? Because this smallest circle belong to the top, and top means higher value. Now tell me here. Suppose this is uh, gamma T1. Okay, this is, let's suppose, Z equal to T1. This is, let's suppose, Z equal to T2. Which one is greater? T1 is greater or T2 is greater? T1 is greater than T2, or T2 is greater than T1? See, this smaller circle here belong to the bottom, right? So T1 belongs to the actually bottom, T2 belongs to top. So T2 is greater than T1, right? Is this fine to everyone? Okay. One circle means one value, and by looking at the at this architecture and this particular contour, you can say that, okay, which is greater and which is lesser. Let me know if that is fine. Okay, great. Now let's just see this. Let's just see this. In this case, suppose I'm getting these kind of contours, which is also fine. In this case, tell me that, let's suppose this is, again, let's suppose K1, this is K2. Which one is greater? K2 is greater than K1, right? Okay. So now you know that which ones are greater, right? By the way, these contours doesn't always look like the circles. Sometimes they might look very weird. For example, in this case, if you cut it, okay, if you cut with respect to the z-axis, if you keep on cutting, in the calculus I've even shown you the 3D visualization. Here it is actually not needed. I'm like the contour shape is not needed, but it could be very different from the circles. Okay, it will depend on, for example, if you have just a box, right, a rectangular box, if you cut that rectangular box, do you think you will be getting circles? No, right? You will be getting the flat plates. Suppose you have something like this as a function. If you keep on cutting it, then you will be getting some contours like this, which are very weird, which is fine. Okay, for this these are the contours, for this these are the contours, and so on. Okay, let's not worry about it. Now, let's solve this question regarding the contour. Suppose they are saying contour or the label curves, I will be keep on, using them interchangeably. Sometimes I can call it contour, which is actually quite popular, and or I can call it label curves also. Okay. Suppose this is the function which is given to me. Now they are saying the label curves of z, which is x square minus y, are what? Okay. So they want us to draw the contours. So what will I do? If they are asking us to draw the contours, then I will be putting the values. I mean, they are actually, they want us to draw for this. For example, I want to draw for 2. I will be putting 2. I will be putting 1 like this. Can you draw the graph for this particular function? Just for this particular function, this is a 2D function, right? So probably you can try to draw it. Okay, this is, I think, y equal to x square minus 2. Okay, which is just like a quadratic function. So maybe something like this. Okay, maybe x square minus 2 will be something like this, right? Is this fine to everyone? So if they ask us to draw the contours, then what you're doing? See, the general function is this is the general function. Tell me in how many dimensions you can make this function. How many dimensions are needed to make this, to plot this function? 3 dimensions, right? X, y, and z. Okay, x value will vary, y value will vary, and based on that, z value will vary. Now tell me how many dimensions are needed for this, or maybe let me just simplify it. For this, if you put a specific value, then how many dimensions are needed? Just 2 dimensions, right? Here it is a 3 dimensional, but if I'm just keeping the z fixed, then it is 2 dimensional, right? So probably you can draw this, right? I mean, you don't need to actually draw, you don't need to know how to draw and all, but I'm just saying that maybe we can put some efforts to draw it. For example, if you don't know anything, then probably you can try putting the values of x equal to 0, x equal to 1, x equal to 2, x equal to minus 1, like this, right? And then see that what is happening with y equal to, let's suppose, minus 2 here, y equal to, let's suppose, 1 minus 2 is minus 1, 4 minus 2 is 2, like this, right? At least you can put some values and see that, okay, what shape it is coming, like that. You can put some efforts to draw it, right? Even if you don't know anything. Okay. Now basically, given this function which was in 3D, if you want to plot the contour, then what you are doing actually, this is the 3D function. If I want to plot the contour, what is the step? The step is to put the values of z, right? Put the values of z. Is this fine to everyone? Okay. And then draw the contours, right? Because these are the contours. See, this is how many contours or label curves? How many label curves it will provide? Just one, right? Corresponding to z equal to 0. It will also provide just one. It will also provide just one. So there will be the contours like this. Okay. For example, you can definitely plot. Now, there is one convention that you should be knowing, and with that, this topic will be closed. Okay, I mean, the contours is just easy. You can just put the values, and you can make the contours. The convention is very important, which says that whenever you are putting the values, okay, for example, you're putting 0, 1, 2, minus 1, minus 2, then it is necessary that you put the values with the regular interval. In the sense that if you're putting 0 and then 1, then don't put 1.5. What is the interval between 0 and 1? What is the interval? 1. What is the what is the next interval? 1. So every interval is 1, right? Don't put don't make the values larger than 1 or lesser than 1. Which means after k equal to 0, if let's suppose I go in this direction, I want to plot for minus something. Can I directly plot for k equal to minus 2? Can I directly plot? See, ideally, I mean, you can plot. Nobody is stopping you to plot. It's not like you can't plot, but you should not plot. Okay, that's the convention. Why that convention is needed, it will get clear. Okay, why that convention is needed, it will get clear in just 5 minutes, right? But for now, just see that the convention is very important, and that you should not be going with more interval which you have defined. It's not that interval should always be 1. From k equal to 0, you can directly plot k equal to 2, but next should be k equal to 4, right? Okay, this is also fine. Okay, so keep them equally spaced. Okay, so let's just see next. Suppose they ask you to draw the contours for this, which is almost same as the previous one, then you can definitely draw for these different values. Okay. Okay. Now, some of you are asking that why that is the case, in the sense that uh, why we want to keep it in the equal spaced, right? Why that is the case. So let's just answer this question, and it is very, very important property of the contour. So currently, this is 3D, but I'm not. I'm not actually drawing it very much 3D. It looks like 2D, but it is actually behind it. You just imagine a mountain, which I'm just showing the front part. Is this fine to everyone? I'm just showing the front part of the function. Now just imagine if I keep on cutting it, okay, if I cut like this, then I will be getting some kind of circles or some kind of shapes, okay? Just imagine I'm getting these kind of shapes. Now, suppose the interval here I'm maintaining is 500, okay? Suppose the interval is 500. Now let's just see this. Here, can you tell me what is the gap in this? In these two, the gap is definitely 500, right? Because I intentionally made the difference of 500 or the interval of 500, right? So this gap is definitely 500. Okay. What about this gap? Just a second. Let me just go here. What about this gap? Can anyone tell me this gap? Great. It is also 500, right? Both are 500 because this is 0, this is 500. So both gaps are 500 only, right? Now you might see that okay, one is 5 here also it is 500, here also it is 500, but these contours are very close to each other, isn't it? These contours are very close to each other. And these contours, I mean, the contour is same, but the distance between these 2 points are little far than compared to this. Why that is happening? Because of the slope. See, here in this part of the function, the slope is basically very low in the sense that it is slowly decreasing. But it is very steep. Just think like a mountain, right? It is very steep. It is like you can say it is a very steep slope, which means if you want to climb up, it is hard here. Is it hard here to climb up? No, right? Comparatively, it is easy. So the very important conclusion which we are making from this diagram is that if if the slope is less, if the slope is less, which means function is decreasing aram say it is decreasing slowly, then if it is zero, then there will be good enough gap for the next level curve, right? But if function is decreasing very rapidly, okay, or increasing very rapidly, I mean, if you go like this, it is increasing. If you go like this, it is decreasing. Whatever you want to say, increasing, decreasing. So basically, function is changing very rapidly. It means what? It means that the slope is very high, right? The slope is very high, and this will automatically result in the less distance of the contour. Okay, so here the less distance should automatically tell you that this is here the steep is high, here the steep is low, right? Is this fine to everyone? So by looking at the distance between the level curve, you should be able to tell, okay, what is the steep here, right? It is high here, it is low here because the distance is good enough. It means function is slowly changing. Okay, I hope that's fine to everyone. Now just imagine that you are not basically, I mean, you are not maintaining the equally spaced contours, which means sometimes you make, let's suppose, from zero to direct 1000, okay, from zero to direct 1000, and sometimes you make from 1000 to 1500. You are not making in between. I mean, you are doing with your choice, right? Let's suppose you are not making these in between. Okay, which means you are going like this. Sometimes from 0 to 1000, from 1000 to 1500, then suddenly 1000 to 3000, like this, right? Will you be able to compare the distances? Which means here you were able to say just for 500, okay, here also 500, here also 500, just to change 500, you are basically change, this will be in the xy, right? I mean, how your x and y will be there. So just to change 500, you have to change actually, or you have to go little far for the x, right? Suppose you are going in the direction of x only. Okay, let's suppose it is the direction of x. It was the direction of y, or maybe it was the direction of your function. Okay, and let's suppose this is the direction of y. This is the direction of z. Suppose z direction currently we don't have the z direction in the contours, or do we have? Tell me, do we have the z direction in the contours? It is just x square minus y equal to 2, right? It is not, or maybe 3. It is not z here. We don't have the z direction. It is just 2D. Okay. Contours is this one only, just 2D. So we don't have z direction, which is fine. But let's suppose I make the contours and I go, I don't have the z direction here. I just have these two directions. Okay. Suppose I'm just going standing here. You can go any direction. You can go here. You can go in the direction of x, y. You can go in strictly in the direction of y. You can go in strictly in the direction of x. Okay. Anyway, if I just talk about strictly in the direction of x, then I'm going too far, right? For 500. Here I'm just going too close for the 500 for just to change 500. So you can compare, right? But on the contrary, let's suppose you draw the contours that are not equally spaced. So you will say, okay, this is 500, है ना? अब इतना ज्यादा समझ नहीं आ रहा कि okay, यहाँ से मुझे अगर 1500 चेक करना है, तो it should be thrice of this. Can you just compare very easily? Do you think you can compare? It should be, let's suppose it is x, it is more than thrice of this, less than thrice of this. I don't think it is easily able to compare, right? Are you getting my point, what I'm trying to say? See, you just want to, how much change you did from here to here? 500 change, right? Now you want to check that, okay, just for the same change, for 500 change, how much I'm making. I mean, in the 500 change in the Z, how much far I'm going in the direction of X. If you want to compare, can you compare very easily? Tell me. It should be 3x at least, like this, right? And okay, it will be little hard. Okay, visually it is not good, right? For visual purpose, it is not good for sure. So that's why let's just keep them equally spaced. Okay. Suppose I keep them equally spaced. Now, if someone asks you that, okay, this is 500, and then someone says, this is 500 also, then probably it will be little easier compared to the previous one. That, okay, yahan pe probably I have moved, let's suppose little, so here I have moved little more, here maybe these two are same or something. Maybe let's suppose slope is constant. Okay, so suppose slope is constant, so it might be same, that's fine. So, but just for visual purpose, I'm saying that it is better that you're keeping the equally spaced, so that whenever the contours are close, you have the alarm alert. What will go in your mind if the contours are close? Oh, the slope is very steep. Steep means very sharp, right? Okay. So if you have very close contours, you will say that, oh, the slope seems to be very steep, right? So that's why let's just keep them equally spaced. ठीक है, कहीं पे 500 के गैप पे बनाया, कहीं पे 2000 गैप लिया, इट्स नॉट गुड. ओके, सो लेट्स जस्ट कीप देम इक्वली स्पेस्ड. Okay, so let's just see what are the key points for the contours. What they are saying, every point on a particular level curve has the same function value. That is what you already know. Although the value chosen for the contour plot are equally spaced, that does not imply that contours themselves are equally spaced. Obviously, it means that these two are close compared to these two. I mean, we are keeping the value of z same, doesn't mean that, okay, contours will be the equally spaced. Closely spaced contours indicate region where the function is increasing or decreasing rapidly. Okay, that's very important. While wildly spaced contours correspond to the location where the function is increasing or decreasing slowly. Okay, if it is closely spaced, then it is basically increasing rapidly. The set of allowable contour value is equivalent to the range of a function. Okay, let's not worry about it. So, by the way, you got the point, right? That if it is closely spaced, then the alarm should be there in the mind that, okay, there are the slope is high, right? It is a steep slope. For example, let's suppose this is some function which was in 3D, but I have put some values of k, for example, equal to 0, equal to 1, equal to 2, equal to 3, like this. I got these kind of points. Can you tell me at this particular point, the slope is high or less compared to this point? What do you think? Compared to point A, let's suppose this is point B, slope at point A is high or slope at B is high? Slope at B should be high, right? It should be high because these are very closed, right? Because they are very close to each other. If they are very close, then the slope should be high. How to verify it? What you can do? You can find the differentiation of this, right? For example, uh, df upon dx and df upon dy. I mean, you can even find the gradient, and then you can check the magnitude of the gradient. Okay, at 0 and at 3 0, you will get to know that which one is high and which one is low. Okay. See, the purpose of this whole exercise is to just let you know what are the contours. Don't worry too much about it. They will not be asking anything directly from it. It is just for our convenience or our visualization purpose. Okay. At least you know that what are these rings mean. What are these means? One ring means the value of function will be same across this whole circle, right? And if the circles are closed, then the slope is high. These are the only two takeaways you need to take. Okay. So let's just do this final question before we wind up the contour discussion. Suppose they are saying that there are some contours which are given. If a person were walking straight from point A to point B, would he be walking up, down, or down? Uphill or downhill? Suppose someone is walking from A to B. You don't know which one is top in the sense that, see here, we have seen these kind of examples, right? See, just by looking at the circle, can you tell that which one is top? That this innermost is top or innermost is down? No, right? I need to tell either this figure or maybe the values will help, right? Suppose I tell the values also. For example, I say, let's suppose I say this K2 is 500 and K1 is 10. Then can you tell me if it is 500, then definitely it is up. K2 is up. 500, definitely you don't need to look at anything. You just need to look at this value. 500 means up, right? It should be up. 10 means down. So K1 is down and K2 is up. Is this okay to everyone? For now, let's suppose I give you this circle, this set of circles, and this set of circles. See, in this particular example, these circles and these circles, these two circles at least look same, almost same, right? But looking at circle, can you tell me that this is upper part of the function or lower part of the function? Just looking at the circle? No, right? So if I tell you the values, let's suppose this is 1000, then if this is 1000, which is let's suppose too high, and this is let's suppose 10, then it is up, right? 1000 means up. Okay. There is no discussion after that. Okay. So similarly, let's suppose, sorry. Similarly, if they say that okay, this is 1, this is 0.25, they are saying you are going from A to B. Okay. So let me just zoom it a bit. Suppose you are going from A to B. So you are going from down to up or up to down? Okay. We are going down to up. Okay. That's fine. Now let's just do the second question. Is the slope steeper at point B? I mean, if you compare B and C, which one is having the steep slope? B and C. Yes. So here it seems to be a little more congested, right? So I think the gap is 0.25. So you can see that here it is little more. So C seems to be steep, right? As compared to B. It is just for visualization. I'm again saying starting C and moving so that X remains constant and Y decreases. Will the ablation begin to increase or decrease? So they are saying X remains constant, which means you will go in this direction and by decrease. Okay. So suppose they are saying if you go in this direction, the function value will be increasing or decreasing. If you go in this direction, the function value will be, see, see, don't say if you go too much, then obviously anything can happen. See, if you go too much, right? Then this is 0.25, then anything can happen. It can decrease also. But tell me just like the immediate one. If you go little bit, okay? Just tell me immediate one. Okay. So basically the function value increase, right? Is this fine? Starting at B and moving so that Y remains constant and X increase. Y remains constant and x increase. So basically, you are saying you're going like this. Tell me, the function value will be increasing or decreasing? It will be decreasing, right? Okay. So mm, these are the answers. It will decrease, increase, point C and uphill. Okay. How it will be decreasing? Because this is 1 here, this is 0.5 here. Okay. If you go in this direction, then it will be decreasing. Okay. So have you understood the contours? At least little bit. And that's all is required for the entire machine learning, right? It is just some curves which are having the same value. The distance will tell you steepness, and also yeah, I mean these are the only two important points. The distance will tell you is steepness, and the value across one level curve is same, right? Okay. Now let's just quickly see gradient descent, and then we will come back to our topic of discussion, which is linear regression with gradient descent. Okay, but before that, we should be knowing gradient descent. So we have just covered, contours. We have not even started the gradient descent. Okay. So gradient. Let me just quickly recall you that what is the fundamental behind the gradient descent that we have already seen. What was the fundamental? We have seen the direction of gradient, right? So this is the fundamental, that if I want to decrease, then I will be going in the direction of the negative gradient. Okay. So if I want to decrease, so that is the basic principle. Okay. This is the only basic principle, and the important principle behind the gradient descent. So let's just start the algorithm. So gradient descent is one method for solving the optimization problem. For example, if you want to find out the minima of, let's suppose, x square, minimum of x square plus 2, okay, which is 2, that because it's very easy function, right? uh you already know this is easy function. But uh, but how to solve it using the gradient descent, right? Let's just check. Okay. So let me just tell you first that why we even need gradient descent. For example for example, let's suppose let's suppose you have some function like this. Okay. Now, if you keep, let's suppose, if you keep f dash x equal to 0, then it is easy to find out the value of x from here. Let's just try it out. 2x log x plus x equal to 1. Is it easy to find out the value of x? Tell me. X equal to something, some 5, 10, or like this. No, right? So it might so happen. See, in linear regression case, was that easy? For example, what is your f dash x? Actually, it was in terms of w. So let me even write in terms of w only. Do you remember this? Here, is this easy to find out w? Yes, actually, yes. So it was easy to find out W here, but it doesn't happen always. Okay. We will see in case of logistic regression, there is, I mean, the next topic we will see, which will be the logistic regression. There, you will get to know that it's not easy to straight away find out the value of W or the parameter, right? Which means you can differentiate. Nobody is stopping you to differentiate. But after the differentiation, if you check that what is the value of W you are getting, then it's not easy to find out in the closed form. Okay. So the closed form, this is called closed form solution. Here you will say closed form doesn't exist. Is this fine to everyone? Okay. So Sudhiram is saying we or means we can say equal to 0, which means yeah, after equating it to 0, you want to solve for x, but it is not always possible to solve for x. So that's why we need some other algorithms where the closed form solution, if the even if the closed form solution doesn't exist, still you are able to solve for, or you are able to minimize or maximize, right? Okay. So let's just see this, which is basically called gradient descent. I mean, one of the way to do it is called gradient descent, which is in the syllabus. So closed form solution are not always available. That's what we have just seen. Okay. So what will I do? Suppose this is a 3D function, or let's suppose just a mountain, and I want to go to the value of the mountain. For example, there's a lowest part of the mountain, right? Suppose I want to go to the valley. Okay, from here I want to move down, 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 sometimes up. It may be sometimes up, but that's fine. Ultimately, I want to go to the lowest part. This is the lowest part. Okay. So that is the idea of the gradient descent, in the sense that I will be starting at some random point, and my goal is to reach at the lowest part. Okay. Great. No, actually, it could be the local minima also. If you encounter some lowest part, which could be it could be local minima also. There is no method which can find out the global minima. Okay. At least I don't know any method which can find out the global minima. Okay. Let's just see the gradient descent quickly. So how does the gradient descent work? Suppose fx equal to x square is there, then you can differentiate it, and then you will be getting 2x. Okay. I mean, the plot is not important. Don't worry about the plot, but yeah, the plot is not important. This is 2x. As I told you already, that here, since it is 2x, and at minus 7.55 or something, it will be the gradient direction will be negative, which means the gradient direction will be this, and here the gradient direction will be positive, which is this. Is this fine to everyone? Sorry, um, the gradient direction is negative. Yeah. So basically, this direction is not the gradient direction; it is the opposite of gradient, minus f dash x. Okay, which means you need to go in the opposite of gradient direction. Okay, so if the gradient is negative, you need to go in the opposite of gradient. Do you remember that if I want to decrease, I will be going in the opposite of gradient? Okay. So let's just quickly do one example. Suppose you are starting at some random point, which is w equal to 12. Let's suppose. Okay. Then what will you do? You will find out the gradient at this particular point, and the gradient, when you find out, will be positive, right? Here it will be positive, so you will move in this direction. Okay, for now let's just keep this as a numerical. Let's just check with this numerical. Suppose this is x square, your initial point is minus 4. Okay, let's suppose I'm calling it x naught. Your initial point is minus 4. Now what is the f dash x? It is 2x, right? So what is the value of the gradient? Minus 8, which is basically in this direction. Minus means in this direction. So now you will go in the opposite of the gradient. So you will go in this direction. So it means you will go means from x naught, you will go means you will add something to x naught. Okay. So what you need to add? I mean, you will be adding some positive quantity or negative quantity. What do you think? Basically, minus 4 say, I think I should be adding some positive quantity, right? Some positive quantity. Then only I will be going in the desired direction. Suppose this is minus 4. Let's suppose I add 3. Then what is my next point? What is the x1? Minus 1, right? So which means if I add 3, then I will come here. Is this fine to everyone? I can even add 30. If I add 30, then I will actually go too far, which is I think 26 or something, right? I need to add positive quantity. It could be 3 or it could be 30 also. But do you think 30 is a good idea? 30 means I will be going to 26 too far, right? Okay. Probably not a good idea, right? So generally we add small values, and how to determine that value, I will just tell you, right? So for now, let's suppose I'm doing this kind of update, that x1 equal to x naught plus, I need to add, right? So suppose they are adding, this is zero point 0.8, right? So okay, zero point 0.8 or 1.6 into 4. Okay. So they're adding 4.8, which is okay. Are they adding 4.8? So, sorry, 6.4. Okay. So they're adding 6.4. How they come to know about the 6.4 and what to add, what not to add, I will just tell you in a minute. Okay. So suppose they're adding some positive quantity, which happen to be 6.4. Okay. So if you add 6.4, right, then your next point will be what? 2.4, right? Is this fine to everyone? So basically, you need to add some positive quantity. That is for sure. How to determine this positive quantity? What they are saying, that that's very interesting. They are saying that you are anyway going in the opposite direction of the gradient. If gradient is negative, you are going in the positive direction, right? So let's just do one thing. This x1 will be x naught. If gradient is negative, then you're going in positive. If it is positive, then you will go in the opposite direction, right? It will be negative. So let's just do one thing. Let's just add minus of grad, okay, or minus of differentiation, or minus of f dash x at x naught. Is this okay to everyone? Can you tell me the value of f dash x here? F dash is 2x, so I think minus 8, right? So it is minus 8. So they are saying you can add minus 4 plus minus 8 means you can add 8, right? This is minus 8, so you can add 8. Okay. But they're saying it might be too high number. Okay. It might be too high number. So let's just generally we multiply it with the some step size. Okay. This is a step size. Step size generally it is in the fraction. For example, they are keeping it 0.8. Okay. But yeah, it will be positive number only because the sign I have taken care here. Okay. Can it be negative? Can the step size be negative? No, right? It will be creating the worst situation. Okay. So it could be some positive number because sign I have taken care. So how they are driving this very important formula? So they are saying since from x naught you will be going in the opposite direction of the gradient, right? So basically in this direction you need to go. So let's just add this quantity directly. But it could be very high number. So generally we multiply by the alpha. This is called gradient update rule. Okay. Or gradient descent update rule. And then we keep on doing it. For example, once we get so this is the update rule. So once we get this x1 which was somewhere here, then we will be doing x2 which may be going here, and sorry, here they are starting with I think a different number, 8.7. Okay, so here this is a different example where they are starting with 8.7. Okay, then in the next step we are going coming down, then coming here, coming here, and so on. Okay, cool. So that's how you will be eventually reaching to your zero. But obviously, it can happen that it might fluctuate in the sense that if your learning rate is not good, then you may go here and there. Maybe I might be having an example. For example, if your learning rate is basically like this, I mean, you if you're taking long jumps, okay, long jumps might not be very useful. Okay, so yeah, there's a fluctuation here also. I think they're converging, but it need not to converge. For example, like this. Okay, you can keep on going here and there. Okay, so it is no convergence. You may keep on going here and there if your learning rate is very bad. Okay, so that's why this alpha is called learning rate. It should not be too high. Okay, let me know if that is fine. Generally near to 1 or maybe 0.1. Generally people keep it 0.1 or something. Okay. So if it is, more than one, I mean, it is not a rule, but I'm just saying if it is more than one, then probably it can diverge also. Okay. I mean, it is not a rule that, okay, because of more than one, it is diverging. Because of more than one, also, it could be converging. For 0.9, it is converging. Okay. For maybe 1.05, also, it could be converging in some case. But generally, people don't keep it very high. Okay. Generally, people keep it how much? I mean, lesser than 0.5. Okay. Just a practical example I'm giving you in the sense that there is no mathematics I'm telling you. Just, based on the practice that people are doing, they generally keep it like this. Is this fine to everyone? So basically, there are two things. One is that in which direction to go. If you're starting from here, then in which direction to go. So who will tell you in the direction in which direction to go? Gradient will tell you, or the direction of gradient will tell you, or the negative direction of gradient will tell you in which direction to go. How much to go? Who is telling you how much to go? Alpha, right? How long to go, in the sense that you should be taking how long jump, it will be given by generally alpha. Okay. So again, there is one example. So instead of alpha, they are using mu, which is fine. So see like this. So they started from 2, then from 2 to 1. Okay, for x square. Then in three iterations 0.25. I think in 4 5 iterations it will be close to 0. Okay. In 4 5 iterations, they are finally getting close to 0. The values of x. Great. Now, how to set this step size, or this is also called learning rate, or a step size. Okay. So how to set this step size? What do you think? Just as I told you, it is people generally keep it not basically, the problem with the step size is that if it is very low, then it will be very low in the sense very slow convergence, right? If it is very high, that might overshoot and even diverge, right? So this is a problem. Is this okay to everyone? Have you understood the problem with the step size? Okay. So obviously, it is crucial to keep it, at some good number, right? Now, what is that good number? Generally, I mean, it will obviously depend on the function, but generally 0.2, 0.3, 0.1, these numbers are good. Okay. So see, this is just right. This is a very good. Okay. Not very slow convergence, not divergence or maybe overshoot or something like this. It is good. Okay. 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 So in general, the gradient descent rule is this, that if you want to update your weight parameters, you will be updating like this. There will be minus sign because I've taken minus here. So W minus eta grad LW. Okay. Okay. Nobody, by the way, nobody is going to ask you what is the step size or what is not the step size. Yes, 0.1 to 0.5 is generally a range. Okay. Obviously, no one can ask you because it's just a practical thing, which means you just uh, see that how your loss function is decreasing. Basically, how your losses is decreasing. Okay, based on the alpha, you can check in the sense that if you are keeping your alpha, something, and then you plot the values of loss function. Okay, first the loss function was this. I mean, the value of loss is this. Now the value of loss is even increasing. Then something happened, even increase more. It means the alpha is not good, right? You can just plot the values of your loss, how the loss is changing across the iterations, across the gradient updates. Okay, as you are moving towards x, which means as you are changing x, okay, from this to this to this, there will be the, you can have one more column which is fx. Okay. So how the values of fx are changing, if these doesn't seems to be very stable, doesn't seems to be decreasing all the time, then probably you need to, little bit disturb your alpha. Okay, just you can just do some practical. Have you understood what I'm trying to say? Right. Okay. So don't worry about the practical implementation. We will be anyway having the different sessions for that. Okay. Now, this is a general rule, which means I will go in the direction of the gradient, and this is the starting point, or maybe I mean the point at the time t. Okay. So if someone asks me that what should be the next point, then the next point is calculated like this. Okay. Let's just do one example very quickly. Suppose there is a function. Okay, they have used a superscript, which is fine. You can use a subscript also. X1 minus 1 whole square plus x2 minus 2 whole square. Suppose this is the function. This function is in x1, x2, right? Now, if someone asks you that starting at the point, this is the starting point 0, 0, and the alpha is given to be at 0 0.1. Someone says that, okay, you start at this point, your step size is this. Can you tell me the x1? What will the x1? X1 will be your starting point minus alpha and your grade, right? So which means your starting point minus alpha and your grade of f. So what is the gradient? With respect to x1, you can do it. It will be 2x1 minus 1, 2x2 minus 2, right? So at 0, 0, I think it will be minus 2 minus 4, right? So minus 0.2 minus 0.4 is your next point. Is this fine to everyone? Okay. Now at this point, do you think you have increased or decreased the value of function? What do you think? Sorry, it is minus and minus plus. So this is plus. I'm sorry about it. Yeah. So basically, if you put 0, 0, the function value was 1 square plus 2 square, which is 5. But if you put 0.2, it will be 0.8 square plus 0.6 square, which is definitely, sorry, 1.6 square, which is definitely lesser than 5, right? I mean, this is lesser than 1, this is lesser than 2. It is definitely lesser than 5. So your function is decreasing, right? I mean, your next point is telling you the function value is decreased. Is this fine to everyone? How we are calculating the next point? Let me know. Okay. Can you calculate one more point? Can you calculate one more point? What will the x2? It will be the x1, which is 0.2, 0.4 minus alpha grade of f, which is 0.2, 0.4 minus alpha is 0.1. Grade was actually this, right? This is the grade. So if you put 0.2, it will be 0.8 minus 0.8, which is 2 into zero point 0.8, right? Minus 1.6. I hope that's fine. 0.2 is 0.8, 1.6 minus 1.6. Yeah. And this will be 0.4 means 1.6 minus 1.6 and minus 3.2. So it will be plus anyway. So it is 0.2 plus 1.6, 0.4 plus, sorry, this is not 1.6 plus 0.16. This is plus 0.32, which is 0.36. This is 0.72. This is your next point, right? Which you are calling x2. Is this fine to everyone? Okay. So basically, how you are finding your x1, x2? Can you do it further? Can you find out x3? Let me know quickly. Yes or no? Okay. You don't need to do it. You can just tell me yes or no. You can do it, right? Based on this, that what we are doing. Okay, great. So if you want to check, you can check the function value of x naught, function value of x1, function value of x2, right? How the function is decreasing. Function value of x naught was 5, I think, right? 1 square plus 2 square. Where did I have written it? Uh, okay, I think I've deleted, right? Okay, anyway, so it was 5 here. It is less than 5 for sure. And then you can calculate here. It is even lesser than, this number. So basically, you will mostly observe. I mean, that's not a ground rule. It might increase, but here in this case, you will observe that generally it should happen actually. That fx naught is greater, basically, or maybe you can say fx2 is even lesser than fx1 than fx naught. This is our goal, right? That the more we go to x2 x3, the we want to decrease the function. This is our goal. Okay, even you can check it here. Tell me, will this always happen? Will this always happen? What do you think? No, right? We have seen that function value might increase sometimes. It's not like it will always happen. For example, from here, if you are jumping like this, then the function value has increased, actually increased by some chance, right? Function value has increased. So function value can increase also, but our goal is to keep on decreasing. Great. Okay. Now, if you look at this gradient descent in 2D, then you can say that, let's suppose you're starting at this W naught, which is this point. As a point you can see, or also as a vector you can see. Okay. So you can see as a point also, as a vector also. Now, interestingly, that's very interesting. Tell me, okay, before I go here, you just need to tell me here. Can anyone tell me that if I'm at this point, okay, if I'm at this point, then gradient direction will be outward or inward? See, the function gradient direction should always be in the function of increase, right? So function is increasing where? So as you can see that this T2 is greater than T1, right? So function is increasing outward. So the gradient direction should be outward. Is this fine? Okay, looking at the values of the contour, you should be able to tell the gradient direction. So this is the gradient direction, which is outward. Why? Because it is the function is increasing. Can anyone tell me here? Here the gradient direction is outward or inward? At this particular point, if I just ask you, then what will you say? See, if you go outward, then function is actually decreasing, right? So the gradient direction is this. This is the gradient direction. Is this fine to everyone? Okay. So just it was just a quick example. Now if I just ask you, looking at this, right? Now you can consider this starting point or any point as a vector, also as a point also. Let me just consider as a vector. Tell me, where will be the gradient? Suppose this is the minimum. Okay. So the gradient will be, or tell me the negative gradient actually in this case, because I want to go in that direction. So will be the negative gradient? It will be actually, it will be like this. Basically, it will be in this direction. Okay. Towards the center, right? Why that is the case? Because it is, why it is towards the center? Because because you can see that, okay, I mean, I don't want to go into the detail here as of now. We will go slowly, but you can see that at this particular level, right, the function value remains constant. Do you all agree? Function value remains constant means that if you go in the tangent direction, okay, if you go immediate tangent, then don't go too much. If you go just very immediate tangent, okay, I mean, this direction actually is circular. There is no circular direction or something. You keep on going in the tangent direction, tangent, 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 and then you will be forming a circle. Do you all agree? This circle is nothing but a made of keep on tangent, tangent directions, right? So you go in the tangent, 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 and finally you will be completing the circle. So basically, the tangent direction, this tangent direction is the direction where the function value is not changing. Do you all agree? The tangent direction is where the function value is not changing, right? So what does this tell you? Can you tell me the gradient direction now? We know the relationship between the direction where the function doesn't change and the direction where the function changes the most. They're perpendicular to each other, right? So the gradient direction will be perpendicular to each other. I mean, this either this direction or this direction. Now, out of these two, we know that it will be this direction. Sorry, negative gradient will be in this direction because we want to decrease. I mean, the decrease direction is this. Anyway, so basically, what I'm saying here is that just two vectors I want to show. One vector was this one, W. Another vector is your this one, which is your gradient, negative gradient, basically. I mean, in this direction I want to go. Okay. So ultimately, your W1 will be W naught minus alpha into grad of f. Okay. Or maybe, I don't know, maybe you can visualize like this. Okay. I mean, basically, you will be adding this W naught, you will be adding this vector plus alpha into this vector, right? Which means, so alpha into this vector could be this much only. Okay. You will be adding these two vectors. Do you all agree? This vector and this vector? Let me know. See, W naught is this vector. Do you all agree? Right? And your and your negative gradient will be something like this. So you will be adding W naught plus alpha into your negative gradient. So if you add these two vectors, okay. So here the visualization might not be too much good, but if you add these two vectors, something like this, okay, probably like this. So uh, okay, basically just imagine something like this. Okay, so suppose this is your W naught, this is your negative gradient. Let's suppose these are the two vectors. If you add them, then there will be a third vector that is W1. So you are going here. Is this fine to everyone? What I'm trying to say? So let's suppose, so this is your W naught, this is your negative gradient. If you add these two vectors, then you will be going in this direction. Is this fine? I mean, ideally, you will be going in the balance of this, right? You're already in W naught direction, and then you want to tilt towards the negative gradient direction. Okay. So if you want to tilt towards this direction, so you will be little bit inclined, right? Little bit inclined. Is this fine? Let me know that how we are getting this W1. This is the space of W1, W2 only, right? There is no Z here. Okay. So now at this particular point, there will be some W1, okay, which is maybe this direction, and your gradient direction is again towards inside. So probably you will be again tilting and you will be again going into some direction. It like you don't need to calculate it about what I'm. It is just a visualization, okay? From here you are going here, then here, then here, then here, then here, and finally you are going here. Okay. So how you are calculating your W2 or any other W1 plus alpha into negative of gradient, right? So you're basically, it is just addition of two vectors. I just want to show you here that is a one vector. It is just also another vector. It is just an addition of two vectors. Okay. So this is how you can visualize the gradient descent with the contours also. So that's why we have seen contours just for this visualization. And also it will be needed later on also. So I thought that we can have those contours here only. Let me know if you have understood this. Okay, great. Now, are you ready to get started with linear regression with gradient descent? Okay, so we have just covered, the little bit of the part in the sense that what is the gradient descent, what is the contour. Now, Now here we will start the topic officially, but we will not just study. I mean, linear. There is actually there is not nothing much to study here, because we will be just having the specific loss function. Okay, so the function will be just specific. That will be the only difference. But we will be studying the gradient descent in with more detail with the help of the linear regression topic. So particularly that's called mini batch gradient descent and stochastic gradient descent, and just a plain gradient descent. Some people also call it, watch whatever we have seen. Some people call it gradient descent, just gradient descent, or some people call it batch gradient descent. Whatever we have seen was the batch gradient descent. Okay, so we will see the variations of the gradient descent also. Okay, so let's just get started. So as you know, the gradient descent is iterative algorithm in the sense that we keep on updating the x and then we finally get to the minimizer, right? I mean, at least we are hoping to get to the minimizer. Like it might diverge also. That's what we know, but at least we are hoping to go to the minimizer. Now, my first question is that why we need the gradient descent? Can anyone quickly tell me why we even need it? Yeah, the first way is the closed form solutions, right? To minimize the loss function we need it. Yes. But we already have the closed form solutions. But why we need it? Because the closed forms may not be possible, right? Yes. And also it might be costly to solve the closed form solutions. So we will see that. Okay. Okay, let's not get much into this, but yeah, I can tell you a little bit about this here. Is that if you, let's suppose, do this matrix multiplication, or maybe you do inverse, or instead of inverse, let's suppose you, at least you will be doing the matrix multiplication, right? So you want to solve for this x transpose x y. You want to solve for this y, right? Equal to, sorry, x transpose x w. You want to solve for w equal to x transpose y, right? You want to solve for this w. So anyway, you will be, multiplying these two. You will be multiplying these two. At least you will be doing this, right? So let's suppose the cost of multiplying these two is n m square. Okay, if you're not much familiar about these notations, don't worry. You will get to know after the data structures and algorithm. So what I'm trying to say here is that, like if you multiply these two, the total cost is, let's suppose, order of n m square, where the x matrix is of m cross n. Okay, and then if you solve the system of linear equation using the Gaussian elimination, then it will take you order of m cube. So actually this m cube and m square, these are costly operations. Okay, so currently if you are not much familiar, don't worry, but yeah, this will come in the data structures and algorithm topic. These are called the big O notation and the asymptotic notations basically. Okay, okay. Now uh, as I just told you that the cost is very high if you directly go for this particular closed form solution. Okay, so the cost is very high, and also the directly solving the closed form also not possible sometimes, right? So that's why we should know other alternatives. One of the alternative is gradient descent. Okay, so it requires multiple iteration, need to choose alpha, work well when n is large. N means number of data points. So if the number of data points are very high, then the size of X will be high or low? Tell me. It will be too long, right? Because there are many data points. So it will be very big matrix, right? So big matrix if n is high. So if n is high, then obviously it will be big matrix, and eventually x transpose x calculation and these calculations will be costly. Okay, so they're offering. So I mean, so basically, if n is large, then they're offering one more solution or one more optimization technique, which is called gradient descent, right? Now, SSV is asking that, sir, if x transpose x is not invertible, then a closed form is not possible, but you can definitely solve using the Gaussian elimination, right? I mean, without even knowing the gradient descent, you can work with that. Gradient descent is not necessary. You can solve using the Gaussian elimination. Okay. So you can check here. Again, the same thing is getting repeated, I think. So see, if you want to solve the gradient is this, right? If you want to solve these kind of equations, then xw and this will take your n into d is, I think, number of features, and n in the number of examples. So earlier it was m into n. Okay, I mean, m was number of features, but yeah, here they are calling it d features. Okay, d is features, n is number of examples. And for this also, n into d you're taking, and then if you are running gradient descent, let's suppose every time basically you need to calculate this gradient, right? In case of gradient descent also, so you need to, if you're running t iterations, then ultimately n dt time you will be taking for gradient descent. And for normal equations you will be taking dq plus n d squares, which we have discussed earlier. This is for Gaussian elimination. This is for the computation of the matrices x transpose x and so on. Okay. So anyway, like basically it is nd square plus dq, and this is ndt or something like that. So we are not going to much talk about this time complexity and all. It will basically depend on the values and so on. But what I'm trying to say here is that we should be having some alternative. Okay. Which one is faster, which one is lower, it will depend on the values of d and t and so on. Okay. If the t is very high, if you are taking too many iterations, then obviously gradient descent is of no use. Okay. So it is the only thing that I want to convey is that I'm just proposing, or we are just having one more optimization technique that can solve even without the closed form, or even without the Gaussian elimination and so on. Okay. So there is one more method which is called gradient descent. So linear regression, yes, this is a plan B, you can say, right? Linear regression have, or maybe any other, any other algorithm, for that matter, might be having closed form solution, and definitely gradient descent always exist, right? So closed form may or may not exist for some problems, but gradient descent always exists, which means you can always solve using gradient descent, right? Okay. So how to update the parameters? I have shown it, with respect to scalars, in the sense that if you have d plus 1 or w naught to wd parameters, then you can update them like this, right? Or if you want, you can show them like a vector format. Okay. W naught to wd, these are the new ones. These are the old ones. Okay. For example, in just one line, you can write this update rule. Okay. So this is called gradient descent update rule. Is this fine to everyone? Okay. Now let's just solve this question and tell me what is the correct answer here. So what they are saying, that let xi yi be the data point where xi is a d-dimensional, which means this is a row and yi is a corresponding column. Okay, tell me, do you really need to worry about augmentation of ones? That where is this one? Am I augmenting one or not? No, they've directly given you the loss function. Okay, they're directly giving you the loss function. Probably they've taken care of this. How they might have taken care? Probably they're implicitly assuming x1 is 1. Okay, or one of the feature is 1. Maybe x2 is 1. Will this matter if x1 is 1 or x2 is 1? That where you are appending this your ones? Will this matter? No, right? So they are automatically taking care of this. You don't need to worry about the bias and all. Okay. They are having the generic forms which are x1 to xn or xd. Okay. One of them could be ones. Okay. So don't worry about the bias and all. Generally, we will not be writing bias again and again because that can be easily taken care with the help of the data matrix. Okay. One of the feature I can keep it as one. Okay. So we want to be again and again saying this is W transpose X plus B, but this ones can be here. So let me just write W transpose X or so on. Okay. So the bias is automatically taken care in the data itself. I have augmented once and finally I'm saying that, okay, this Xi is a D-dimensional. Okay. Anyway, so this is a loss function, which is a popular loss function. What do we call it? We call it, can anyone complete me? MSE, mean square error, right? I think it's not mean, but ठीक है चलेगा. This they have just divided by 2, but that's fine. Okay, that's like that's fine. Don't worry about it. Don't worry about the constants. Okay. So now what they are saying, if you differentiate this with respect to what is the correct expression for the partial derivative? Okay. So they're asking you just to differentiate with respect to wj. Just tell me, can you write it like this? Wi minus w1 x1 plus w2 x2 plus w3 x3 like this, right? Whole square. So what is the correct answer here? If you differentiate this with respect to, let's suppose, W2, if you differentiate with respect to W2, this whole term will come. And so, okay. So actually this xi is there. So let me write xi1. Okay. I throw I2 like this. Okay. For wj, what is that? Xij. Okay. Because I throw is there and now I'm changing the column. Is this fine? The notation? Is the notation clear to everyone? That what I'm saying? X is one data point, and then across this data point only, this I throw, right? This is xi. So it might be xi1, xi2. I want to just open up within the row. Okay. So if I open up within the row, then it will be like this. Anyway, if you just differentiate with respect to wj, then I think 2 into this whole quantity, 2 into this whole quantity minus xij. So what is the answer? I think B is the correct answer, right? So let's just check. Yes. So I think 2 and 2 is getting cancelled out. So that's why probably they have already put it 2. Okay. So that they don't want to put in the options, which is fine. So answer is B. Okay. Okay. They have also used the similar notations that I was using. Great. Is this okay? Let me know if that is okay. Now, if someone asks you, given this, can you write the gradient update rule? So probably you can say for wj, if someone asks you, let's suppose just for wj, then it will be wj minus alpha into this one, right? This is the gradient update rule for wj only. Okay. And what is the value of this? You have just calculated it, right? Okay. But gradient descent is also slow. What is the reason behind it? So anyone wants to guess that why you think the gradient descent is also slow? See, let's just call see whatever is inside, okay, whatever is inside this one quantity is for one data point or for multiple data points? Just one quantity. Tell me, just one quantity. This, only this. Just for I, right? Just for I th data point, isn't it? So we are summing over all the data points. Let's suppose there are m data points. Okay. So here we are summing over all the data points. You divide by 1 by 2 or don't divide by 1 by 2, doesn't matter. But yeah, we sum over all the data points. That is very important point here to notice. Do you think that it is practically even possible? There are millions of data points, right? So this is important quantity. This is for ith data point. Okay. So if you want to calculate, let's just call this particular for just one data point, I'm calling it loss. And then if you're summing over all the xy or all the data points, then we are calling it, I think, train loss. Okay. Are these two terms okay to everyone? Little bit new in the sense that just for one data point, I'm calling it loss, just to make sure our, writing purpose is convenient to everyone. So just for one data point, I'm calling it loss. For all the data points, I'm calling it train loss. This train losses, if I sum over all the data points, right? Now, if you calculate, see, this is the update rule in the gradient descent. Is this okay to everyone? And we need to keep on doing it for some iterations. Okay. Let's suppose for 10 iterations, I'm doing it. Okay. Or for 50 iterations, I'm doing it. So if you check it, then what is happening? That I'm updating my W like this. W minus eta into gradient of the train loss, which means I need to calculate the train loss again and again. For all the data points, I need to calculate the loss. That okay, if I adjust, okay, based on the old W, what is the error? The first data point is incurring based on this W, right? Based on the old W. What is the error? The second data point is incurring. What is the error? The third data point is incurring, and so on. I need to add for million data points. Is this even possible to load? Okay. Uh, Probably you don't want to load all of the data in the memory at the same time. Actually, I don't want to go into that detail, but I just want to ask you if you want to think in that terms. See, if you want to compute any computation, what is the first step? You need to load that particular data in the memory, right? I mean, you can't do it in the hard disk or in some other memory. So you need to load that in the memory. So actually it is obviously not practically possible to have that much large main memory also. Anyway, like, let's not worry about it. So but in the terms of the memory, if you don't want to talk about it, let's just talk about in the terms of at least time. Don't you think summing over 1 million will be too much time taking? Definitely, it will be too much time taking if m value is 1 million, right? So that's why the elephant symbol is there. The gradient descent is slow. Okay. So we have one more algorithm which is called. So here the problem is that each iteration required going over all the training examples expensive when we have lots of data. Okay. This slide I have taken from Stanford. Okay. Cool. So limitations of the gradient descent. So far, we have seen gradient descent as a general purpose algorithm to optimize the training loss. However, one problem with the gradient descent is that it is slow. Recall that training loss is sum over all the training data. If we have 1 million training examples, each gradient computation required going through the 1 million examples, and this must happen before we make any progress. So basically, before updating the W, I need to make sure that I'm summing over 1 million points, right? Can we make progress before seeing all the data? That is the question. Okay. And that's where the stochastic gradient descent comes, which is little different from gradient descent. So now if you observe what is the difference between the stochastic and the gradient descent, then it will be very much clear to you by looking at this formula. Let's just call this inside the quantity just for one data point. I'm calling it loss, right? Just for one data point. Okay. So what I'm saying here, that we are not using train loss for the update. We are using just a loss, which means what I'm saying that uh, that earlier what I was doing, I was running these iterations, which was fine, but I was not having this loop. I was just saying that okay, here I was having train loss. If you just compare, if I just ask you to compare, if you put them side by side, then you will get to realize this, that what is the difference between earlier one and this one. Okay. Except that the images of elephant and the birds, there is some significant and serious difference, right? Okay. So what is the difference? Here, if you see that you are using train loss, right? You're using train loss for your update, but here you're using just a loss, which means if you want to update your W, what you can do, you can take some data point, you update your W. Okay. I mean, don't worry about this iterations and all for now. So you keep on basically you're updating your W just based on one data point. Is this fine? Where I'm saying some, I'm saying one, right? I'm saying one data point. Only one. You're just taking one data point and you're updating your W. So if you do it, right? If you do it, then you're updating your W without seeing all the data. Is this fine? Right? Which means you're saying that what does this intuitively mean? It means you are saying your W is some value. You are saying, okay, I want to decrease the loss, but not by looking at the whole examples, not by looking at all the training examples at the once. I'm looking at just one example. ये मुझे जो बोलेगा, whatever this example is telling to me, कि okay, just go in this direction, in the sense that okay, the gradient should be this. Whatever this example is telling to me, I'm just optimizing for just one example. I'm just being nice for one person only. Okay. Can I be bad at the same time for other persons? Yes, it is possible. Okay. It is possible to go bad for other persons if I'm just making favor in the for the one person. But that's what this algorithm says. That okay, just update your W just based on what someone just one person is saying. Okay. So here I'm updating W very quickly, right? Here I'm updating W very slow. So that is the only difference. How it is helping? Because it might converge faster, in the sense that if you check f of w1, f of w2, I mean how your loss function, okay, or L or whatever you want to say, okay, how your loss function is changing. So here you will say that okay, after 10 iterations, or maybe generally if I just compare, let's suppose after 100 iterations, you are achieving very low value. Okay, generally you are achieving very low value. Here even that value is not achieved after, let's suppose, 5 iterations also. By the way, here 5 iterations and here these 100 means what? Let's suppose these are 1 million example. This 5 iterations means total 5 million, right? Because you are calculating over 1 million, so total 5 million computations you are doing. But here 100 iterations means just 100 iterations. Okay. So this 100 is actually very less, I mean very light. These 100 are very light compared to these 5. Do you all agree? Even this one iteration of the gradient update is very costly compared to 100 iterations. Do you all agree? Even this one is too costly, right? So basically, how it is helping us? It is just helping us to achieve the minimum value faster. Okay, so it is observed that stochastic gradient descent generally, obviously, it is not. I'm not saying it will always happen, but it is observed that generally it is basically achieving the convergence faster. Okay, compared to the gradient descent. We will see more things. Don't worry. Yeah, you can select the point randomly. Yes, it is a randomly point selected, or maybe you can go in the iterative fashion in the sense that okay, first point, second point, third point. Again, there are different versions. Okay, you can select random. You can call it randomized stochastic gradient descent, or like that. Okay, so the general idea is that we will be updating on one point. How you are selecting on a point, it is up to you. Okay, how you are selecting the point, it is up to you. But yes, we are selecting one point. That is what stochastic gradient descent is saying. Okay, don't worry. There are many doubts. So we will be having, as I told you, we will be having 20 to 25 questions. Okay, and those questions are taken from various top universities, and those questions are just based on the gradient descent. Okay, just the comparisons. Okay, between these two algorithms, just the comparisons, and out of after doing all those questions, your all of your concepts regarding these two algorithms will be clear. Okay. Cool. Now let's just move to the next variation. So basically, there are, as I told you, there are three variations. One is gradient descent or batch gradient descent. Okay. Another one is stochastic, which we have seen. There is one more, which is called mini batch. Can anyone guess what it could be? This is between the gradient descent and the stochastic. What it could be? Yes. So we will be taking some few, not all, not just one. We will be taking some few examples. Okay. For weight update. For example, for batch gradient descent or just gradient descent, actually, some people call it batch gradient descent, some people call it gradient descent. I hope that's fine to everyone. Okay. So we will be taking all in batch gradient descent. In mini batch, we will be taking some. In the stochastic, we will be strictly taking just one. Okay, that's the only difference. Now, batch gradient descent and stochastic gradient descent, there is one comparison with respect to how you are achieving the loss. So you started from here, and then let's suppose you're going here, 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 here. So you can see that okay, that here you are going in the 1, 2, 3, 4, 5, 5, 6 iterations. Maybe you're taking 20, 30 iterations here, but still, which one is better? Here, let's suppose you're taking 30 iterations. You are going. See, by the way, one thing you can observe, it is very smooth, right? It is very smooth. Is this smooth? No, right? See, here I'm changing the direction of W based on one example. I know someone said me go here. Then another one said, oh, you minimize loss with respect to me only. You take care of me only. Then you go here. You go here like this. Okay, it might be having too much of variations. Okay, too much of variations. But here the gradients are very stable. The directions are very smooth. Okay, because it is in the harmony. It is in the monotonous. Everyone in one voice. Okay, they are saying go here like this. Okay, they're screaming at the same time, go here. Okay, but they're screaming different. No, no, go here, go here. There's too much of fuzz, right? Too much. Everyone is saying different things whenever we ask them. Okay, so maybe there's too much of fluctuation here, but this is very smooth, right? Is this fine to everyone? Okay, should it not take more or less same time? uh Obviously this is 1 million examples. How it can take same time, right? How it can take same time? It is too many examples. So here I just wanted to show you the visualization. Okay. Yes, it is less efficient. So, but generally, it is just a practical thing that I'm telling you. Generally, people have observed that okay, let's suppose if it is converging, if it is converging, let's suppose in 5 or 10 iterations, then probably it is converging. Let's suppose in 100 iterations. Okay, but in 100 iterations here are still very light compared to these 10 iterations. Just a practical thing. Don't worry too much about it. Okay. So what I'm saying here is that just observe the smoothness. Okay, this is one thing that you can definitely observe. Okay. Now, if you talk about the mini batch, this color is showing mini batch. So you see here too much of variations, right? Too much of variations. Oh my God, what is happening? That is definitely not the gradient descent. This is stochastic. This is very harmony in harmony. Everyone is saying go here, go here, go here, go here like this, right? Now the mini batch is the between, right? Is this too much of variation just like stochastic? No, right? Neither it is very smooth. So it is a mini batch. Understood? This I have taken from Illinois University. Okay. See, just for the visualization purpose, although they might not ask these kind of thing, but just you should be having the better feel, okay? Because whenever we doing the questions, now your mind know that okay, there is too many variations of the gradient in case of stochastic and like that, right? Your mind know these things visually in a better way, right? Now you can answer questions. You will see the difference that okay, now you have the visualization. You will see the difference in solving the question. So that's why I thought that we should be having the contours. Okay. So actually the contours, they will most probably they might not be asking, and there is not a way, not a good way to ask a good question from the contours. They generally, I don't think they will be asking. If they ask, it is good for you only. But yeah, for our teaching purpose, it was necessary. Okay. For our teaching purpose, it was necessary to know contours and all. So Navjot is saying that how do we stop in the gradient descent? Yes, the number of iterations is one thing that is a good question. Basically, I would say, right? That how do we decide the number of iterations? So what is your guess? What do you people think? How we might be deciding about the number of iterations? Maybe we can see that how the loss, yes, how the loss function is changing. For example, one of the ways that you can check the gradient, right? If the gradient is almost equal to zero, so instead of the fixed iteration, you can have uh like some people have like this. So instead of fixed iterations, some people have like this. They say while, instead of for loop, they say while gradient of the train loss is mm, almost equal to 0.8, 0.5. I mean, or almost equal to means less than, greater than, or maybe the mod of this is less than or equal to 0.5, something like this. Okay. I mean, they say it is approximately 0.5 or lesser, then I should stop. Okay. I mean, this is stopping criteria is up to you. Okay, don't worry about it. The number of iterations, you can fix the number of iterations to be 10, 20. Okay, you can just run, you can just plot the graph in the sense that, okay, how the loss is changing. For example, this is loss, this is the number of iterations. You can see that, okay, the loss is changing after, let's suppose after 10 iterations, you find out कि loss तो slow आराम आराम से चल रहा है, इतना time है नहीं. Okay, so you can say कि 10 is the good number, let's just stop at 10. Okay, whenever you see that, okay, initially loss was decreasing whenever I'm going in that direction. Initially loss was decreasing too much, but after some time it is like okay, very slow increment or very slow basically progress. You can say okay, let's just stop at 10. Okay, I don't want to do it any further. So it is up to you how you are deciding the criteria, stopping criteria. Okay, maybe you can plot the graph, you can keep on plotting the graph, or these kind of things are uh, can be done, which means you can see that okay, if the gradient value is within 0.5, then I will stop. Okay, this could be one criteria, this could be one criteria, or even you don't see any of this, you will say okay, I have very strong intuition. Generally people do it for 10, 15 iterations, so let me also do it for 15 iterations. I will blindly put it 15. Okay, that's also fine. Okay, the stopping criteria you can decide, right? Okay, so Navjot is saying that how do we know we have reached the global minima or the local minima? Global and local you can't know. Okay, there is no way to determine that whether you have reached the global or local. But fortunately, for example, we have the linear regression or any other problem. There we have the convex optimization problems. So we will see about the convexity little bit here because we have already covered in the calculus. So if the loss function is convex, there is no local. I mean, there is always global. एक ही मिनिमा होगा उसमें. फॉर एग्जांपल इफ दिस इज अ कॉन्वेक्स फंक्शन, right? So this is only one minima, which is local, global, whatever you want to say. So fortunately for most of our loss functions, we are having the convex loss functions, okay, which will be having just one minima, right? Okay. So is this fine to everyone? Now similarly, the stochastic is fluctuating too much. Batch gradient, let's suppose like going like this, mini match is going like this. Okay. How will it be in real life? This is real life only, right? How it will help in real life, you want to ask? Okay, can you write your question properly? What help? Okay, so again, there are many visualization I've taken. This is from Cornell University. Okay, so here, let's just assume your origin is this. Okay, maybe, and your w naught is this, and your gradient is also this. So basically, you moving like this only. Okay, you're moving in one direction, assuming your origin is this, something like this. Anyway, so I hope you got the point that that here in mini match there is less fluctuation in stochastic, too much of variation in batch gradient or just a gradient descent. There is a less fluctuation. Okay. 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 So Sumaya, can you please write your doubt for now? So Ijaz is saying that how will it help in the real life if there is only one minima? If only one minima is there, but in reality there can be many. No, in reality also there is one. For example, in mean square error function there is just one, right? In reality also there is just one. In MSE there is only this is a convex function, convex loss. Okay, this is just one minima. If there are many minimas, then you just want one of them. Okay, whether it is a global one, you can't say. Okay, you can't say it is a global one or not. But generally in machine learning, we will be dealing with the convex optimization problems or the convex functions, where we just have the functions will be like of this shape, where we just have only one minima. Okay, so let's just solve this question. Tell me whether it is true or false. The object after gradient descent update step, the objective function value at the weight vector is always lower after the update than before. This is definitely false, right? False if the step is too large, the objective value can increase after an update, right? Okay. Is this okay to everyone? Let me know. Okay. There is always a unique steepest descent direction in the gradient descent. That's an interesting question. See, it was negative of gradient, right? So there is always unique, or there could be, different directions. So actually, it was a bit of this was covered in the calculus. So don't worry, I might be covering it tomorrow also. So if the gradient along some dimensions are zero, then there won't be a unit direction. Okay, the unit steepest descent won't be there if the gradient along some dimensions are zero, which means that if let's suppose the gradient among all the along all the direction is zero, it means that you go in any direction, you will not be able to increase or decrease the function because the gradient is zero, right? Let's suppose it is zero across all the dimensions. But if it is zero in just one dimension, let's suppose across the along the x-axis it is zero, which means del f upon del x is only zero. Everything else is, let's suppose, non-zero. So basically, with respect to x, you go in this direction or this direction doesn't matter. Okay. So if del f upon del x equal to 0 and everything else is not 0, okay, let's suppose everything else is non-zero. So with respect to y, obviously you need to go in the negative direction of this, minus of this. But with respect to x, you can go in any direction of this. Okay, I mean you can go like this, you can go like this. Okay, these are the two possible directions here. Let's suppose with respect to x and with respect to y it is 0. Then in these two dimensions you can go anywhere. Okay, I mean you choose any value in these two dimensions, and then in the third dimension or in the rest dimensions you need to take the specific directions only. Okay, is this little bit clear to everyone? Right. Okay, now let's just see this. So let's do one thing. Actually there I think I don't remember the count, but let me just see. Okay, this is 37, but I think there are many other questions also. I think there are 20 to 25 or maybe 30 questions are there. Okay, which are good questions. So there are, approx 30 questions I have selected from many different universities. Let's just do one thing. Let's solve all of these questions in a new session. Okay. So do you want it to today or the session to be conducted today or tomorrow? Okay, so we can solve all of these 30 questions, whatever we have tomorrow, and then you will be having the better grasp on these two algorithms, which is, I mean, these three algorithms, which is gradient descent, mini batch, or the stochastic. Okay, so the idea is that, like what I'm thinking that for each and every topic, I will be covering at least 20 to 30 questions. And if I assume that there are, let's suppose, 20 topics, okay, overall in the gate DA, then I'm just in one course I'm thinking to cover more than 500 questions. Okay, 500 to 600 questions just in the course itself. So the idea is that if we cover these many questions, if we cover 20 to 30 questions just for each and a small topic, then at least the machine learning part, for the machine learning part, you will be ultra confident that okay, you know the things, right, in a really good detail. So you might have seen the difference, right? For example, if you are seeing the linear regression before questions and after questions, then there should be some significant difference. Similarly, these questions for the gradient descent I have taken from very good universities. Okay, so after solving these questions, you will be very confident, right? So I've taken these questions from the top-notch universities like Berkeley, Stanford, and so on. Okay. So apart from your marks, your machine learning marks, I will also say that once you do this course thoroughly, your knowledge about the machine learning will also be improved too much. Okay, great. And also, like the machine learning course might go little slow in the sense that I might be having two classes and then one off. Okay, so that I also get time to prepare for the questions and all. It actually takes a lot of time. So I will be taking two class and one off, and in parallel there will be one more subject. For example, currently DBMS is going on, and then DBMS warehousing will go on, and then there will be artificial intelligence and so on. So in parallel there will be always one subject, but I'm thinking to take this machine learning little longer than expected, but obviously in the parallel there will be one more subject always. Okay, so that your syllabus doesn't get delayed. Your syllabus will definitely be completed within the predetermined timeline. I think it is by the end of October. Okay, your syllabus won't be delayed. You will be having two subjects at a time. That is the only difference. Okay, I mean, whenever there is a off, you can just cover the remaining the parallel subject. Okay, so thank you everyone. Thank you so much. Take care. If there is any doubt, you can just let me know. Let me just stop the recording. If the doubt is such that I want to cover in the video, then I will just resume the recording again. Okay, thank you everyone.